right, so for question 24, they want to know the hybridization of both of these. So I've got bromine pentafluoride and arsenic pentafluoride. So bromine's got 7 electrons, right? I've got 5 fluorines, 7 electrons each. So that's 35, that's 42 electrons to assign. Arsenic, and then I've still got 5 fluorines, so 5 fluorines can be 35. And I think arsenic's in the same family as nitrogen, so that would be 5, so 40 electrons. So I'm going to start with putting the boron, the bromine in the middle. I've got 5 fluorines, so 1, 2, 3, 4, and 5. And that's 10 electrons. So it's going to give me 32. Yeah. So I'm going to put those 5 fluorines, 1, 2, 3, 4, 5 fluorines out there. So I've got 42 electrons. I just assigned 10 electrons. I've got 32 left. I'm going to fill the octet. Right, there's 6, there's 12, there's 18, there's 24, there's 30. So got 2 electrons left. Those last 2 electrons are going to go on bromine. And then for the arsenic pentafluoride, right, we're going to put arsenic in the middle. 1, 2, 3, 4, 5 fluorines. So I just assigned 10 electrons there. I've got 30 electrons left. I'm going to fill the octet of those fluorines. So there's 6, there's 12, there's 18, 24, and 30. So for the bromine pentafluoride, got 6 electron domains. 6 electron domains means I have to have 6 hybrid orbitals, right? So we're going to mix together S, my 3 p orbitals, and 2 d orbitals. So the bromine pentafluoride is sp3d2. As for the arsenic pentafluoride, 5 electron domains, 5 electron domains, 5 hybrid orbitals. We're just going to be sp3d because of that. For question 24. For question 25, right, shown below are some data for a series of experiments performed in a sample of argon. Which one of the gas laws is illustrated here? So if we take a look, right, we're not changing moles. Moles stay constant, so it's not Avogadro's law. We can cancel that out, all right? Temperature is also staying constant, right? So if we look, I've got 1 atmosphere, I go to 2 atmospheres, I go to half an atmosphere, and we notice that between 1 and 2, right, my volume changes as my pressure increases, and as my pressure decreases, right, my volume changes as well. So whose law talked about the pressure volume relationships of a gas? Yeah, it's Boyle, right? Charles' law looked at the temperature, right? So Charles' law was temperature, Boyle's law was the pressure volume relationship. So yeah, Boyle's law, right? We didn't do that. Gay-Lussac's law we talked about, that was temperature and pressure. And yeah, we didn't really talk about Dalton's law. So yeah, Boyle's law for question 25. For question 26, all right, question 26, now our pressure stays the same, our volume changes, our temperature stays the same, and we're changing the number of moles. And as we're changing the number of moles, right, the relationship between moles and the volume of a gas was Avogadro's law. So that would be choice B for question 26. And Sophie, sorry. No, as long as you know PV equals N, R, and T. Because like I said, we didn't spend much time on chapter 10. PV equals NRT is the biggest. We kind of covered each Boyle's law, Charles' law, Avogadro's law to show how they come together to form PV equals NRT. But you don't need to know whose law was whose on the real exam. Question 27, right? Oh, okay. The rate of effusion, this is tied to root mean squared speed, right? So root mean squared speed 3RT over M. Basically, the faster a gas is moving, the faster it's going to effuse, because effusion is like a gas. If you fill up a balloon, right, you come back 3 days later and that balloon is shrank, right? The balloon is shrank because the gas molecules are escaping, right? The little microscopic openings in the polymer of the balloon. And so the faster the gas molecules are moving, right, the faster they're going to be able to escape, because they're going to have more collisions with that membrane, the balloon, basically. The slower gas molecules are moving, they're going to have fewer collisions. They're not going to escape as fast. They're not going to effuse as fast. So rank the following gases in order of increasing rate of effusion. So, right, smaller molar mass will escape faster because it's moving faster. Because moving faster, you're going to have more collisions. So let's see which one of these is the lightest one here. So increasing rate of effusion, basically heavy to molar mass. So HBr is like 80 grams per mole. Oxygen is 16, so 26, 28 grams per mole. Sulfur is 30, maybe like 34. Chlorine 35, so like 70.9 grams per mole. All right, what was the sulfur? Sulfur's 32, so yeah, 34, and then sulfur hexafluoride. Sulfur is 32, and then 6 times 19 plus 32, 146. Thank you, Green. So heaviest would be the sulfur hexafluoride. That's going to effuse the slowest, followed by HBr, followed by chlorine, followed by hydrogen sulfide, followed by carbon monoxide. Should be the fastest to effuse for question 27.